Okay, so we're going to do the solution of exercise 12. So f of z is supposed to be az plus b all over cz plus d, where a, b, c and d are real and ad minus bc is equal to 1. F of 0 equal to 0 is equivalent to requiring that b should be equal to 0, and then I have that f of z is of the form az divided by cz plus a minus 1, because I have the condition a times d minus b times c is equal to 0. Now if I calculate f prime of z, this is equal to a cz plus a minus 1 minus ac z divided by cz plus a to the minus 1 all squared, so that f prime of 0 is equal to 1 divided by a to the minus 2, which is a squared, and hence I get that f is 0 is hyperbolic repulsive, given only if the absolute value of a is greater than 1, hyperbolic attractive, given only if the absolute value of a is less than or equal to 1, and parabolic, given only if a is equal to 1, because I can multiply by minus 1 in the other case. Okay, so now I claim that for all n, f the n of z is equal to a to the n z divided by c a to the n minus 1 up to a to the 1 minus n, so this would be plus a to the n minus 3, so we're going down by 2 each time, times z plus a to the minus n. Okay? And obviously we're going to prove this by induction on n. So proof by induction on n. True root for n equal to 1. Okay? So now, suppose that I have f of n of z equal to a to the n of z divided by c. This sum, a to the 1 minus n of z plus a to the minus n, then f of n plus 1 of z is equal to a to the n plus 1 z divided by c a to the n minus 1 up to a to the minus n z plus a to the minus n divided by c times a to the n plus 1 of z divided by c a to the n minus 1, sorry, a to the n of z plus up to a to the 1 minus n of z plus a to the minus n, and this is all plus a to the minus 1. So now I'm going to take this huge and nasty fraction and multiply all the terms by this expression downstairs here, and this gives me, here on top I get a to the n plus 1 z, and here I get c times a to the n z plus a to the minus 1 c times a to the n minus 1 up to a to the 1 minus n times z plus a to the minus n minus 1, which does indeed give me a to the n plus 1 z divided by c times a to the n plus a to the n minus 2, and so on down to a to the minus n times z plus a to the minus n minus 1, which was what I wanted. Okay, so now let's look at the parabolic, the convergence in the parabolic and hyperbolic attractive case. Okay, so suppose I have a is equal to 1. Then I get f the n of z is equal to z divided by 1 plus nc of z. Okay? And this gives me that fn z, I suppose that z is different from 0, and I look at the rate at which it converges towards fn of z is approximately 1 over nc. Okay, now suppose I have a different to 1 and absolute value of a less than equal to 1, so that my an n minus 1 plus a to the n minus 3 and so on down to a 1 minus n I can write as being a to the n minus 1 multiplied by 1 plus a to the minus 2 and so on, right way down to a to the minus 2 times n plus 1, which is equal to a to the n minus 1 divided by 1 minus a to the minus, this should be an n minus 1, n minus 2 n divided by 1 minus a to the minus 2. Okay, which is equivalent as n goes to plus infinity to a to the n minus 1 divided by 1 minus a squared. So what I get here is that fn of z is equivalent to a to the n of z divided by a to the minus n plus a to the n minus 1 all over 1 minus a squared of z. Sorry, with a c here. Okay. And the thing you should be concentrating on is that here we have a decrease that is exponential in a, in n.